We're going to take a look at number 15 on projectiles launched at angles. In this one, a ball is thrown from the top of a building that is 100 meters high. It hits the ground 10 seconds later, so it takes 10 seconds to get to this spot here, 50 meters from the base of the building. So this distance here is 50 meters. Obviously, this is not drawn to scale. Find all the kinematics quantities, the D, the V naught, VF, A, and T, for both directions, X and Y, for the following positions. The initial position when it's thrown, the maximum height position, the range position, which means when it gets back to the starting height that it was thrown from, so that would be right around here, the final position just as it's about to hit the ground, and also find the velocity of the ball at the instant it becomes a projectile. So we can start with the initial position if we like. So in order to do that, we're going to have to solve for the velocity in the X and the velocity in the Y when this thing gets thrown. We do know that if we take a look at the final position information, we'd be able to solve for velocity in the X and initial velocity in the Y because we actually have enough stuff to do it. So before we can move on to the initial position, it might seem counterintuitive, we're going to actually find some things from knowing the final position. We know the final position in the X direction is 50 meters because it's at 50 meters away, and in the Y direction, negative 100 because it lands on the ground 100 meters below. It's said it takes 10 seconds for it to hit the ground, so that's my time in the X and time in the Y, and the acceleration in the Y direction is negative 9.8 meters per second squared. We actually have enough information here in the X and in the Y to solve for the initial velocity and also the final velocity in the Y direction because it does ask for every quantity for all positions mentioned. Solving for the velocity in the X direction, velocity is distance over time, so 50 over 10. Shouldn't even need a calculator for that. The velocity in the X direction at all times in this problem is going to be 5 meters per second. In the Y direction, the initial velocity, which will be the initial velocity for every other spot, because we're always talking about initial velocity is the velocity when it was thrown. We're going to use the third equation to do this, solving for initial velocity. So we're going to subtract 1/2 AT squared over to the left side, which is why we have D minus 1/2 AT squared. And then to get V naught by itself, we're going to divide time, which is why it's in the denominator. We can plug in all of our numbers, negative 100 for D, negative 9.8 for acceleration, and 10 for time. Don't forget to square it in the top. And that gets us an initial velocity of 39 meters per second. The final velocity, when this thing is going to hit the ground in the Y direction, can be found using the first equation, V naught plus AT. So 39 plus negative 9.8 times 10 gets us a final velocity downward negative 59 meters per second. So now if we jump down to the initial position, the displacement is nothing because it hasn't actually gone anywhere yet. We know that the moment it leaves your hand, the velocity in the X direction is 5 meters per second. The initial velocity is 39 meters per second. And since it's the moment it left your hand, no time has passed, so there's no time to find. And the final velocity would just be the same as the initial velocity because it hasn't gone anywhere yet. So that's the initial position. That was pretty easy to do. If we're going to take a look for the maximum height, again, the X velocity, 5 meters per second, and the initial velocity in the Y direction, 39, remain unchanged at every position. At maximum height, the final velocity is 0 meters per second, and the acceleration is negative 9.8 meters per second squared. We're going to find the time in the Y direction as well as the D in the Y direction. But once we find time, we'll be able to use it in the X to solve for how far out it goes in the X direction, so how far this way it's going to go when it reaches the maximum height. And we'll find the Y displacement, which is how high it's actually going to go from the building. So if we wanted to go from the ground, we would just add 100 to our answer. To solve for how high this thing is going to go, we would use the fourth equation because we don't have time yet. So VF squared equals V naught squared plus 2AD. Solving for D, I'm going to subtract V naught squared over to the left, which is why I have VF squared minus V naught squared. And I'm going to divide the 2A over to the left, which would give me the 2A in the denominator. Plugging in my numbers, 0 squared minus 39 squared divided by 2 times negative 9.8 gives me a displacement of 77.6 meters. Again, that would be how high it's going to go from where it was thrown. If you're answering this problem for how high it goes from the ground, we would just have to add 100, which is the height of the building, giving us 177.6 meters. If we want to find out how long it's going to take to get to the maximum height, we can use any equation we want now because we have D, V naught, VF, and A. I chose the first equation because it's probably the easiest one on there. Just going to subtract v naught squared over to the left and then divide by a. So I have vf squared minus v naught squared divided by a equals t. Plugging in my numbers, 0 minus 39 divided by negative 9.8 gives me a time of 3.98 seconds for this projectile to reach the maximum height. The range position means the position when it returns to the starting height. So that would be somewhere right around here. In the range position, we know that the velocity in the x stays unchanged the entire time, so that's 5 meters per second. The initial velocity in the y stays unchanged, which is 39 meters per second. The displacement in the y direction is 0 by definition for the range position. The acceleration is negative 9.8, and you might be wondering where some of the rest of these numbers came from. Did we solve for them? How do we figure these out? Well, the range position, by definition, is going to be twice as far in the x direction as the maximum height, because as long as it takes to go up, it's going to take that amount of time to come back down, and the amount of distance it travels to the right on the way up is going to equal the distance it travels to the right on the way back down. So if I know that my maximum height, my displacement in the x direction is 19.9, I know I just have to double that in order to find my displacement at the range position, since it's twice as far away, which would give me 39.8 meters. Similarly, if I know it took 3.98 seconds to go up to the maximum height, it's going to take 3.98 seconds to come back down to the range position. So if I double my time, I know my time is 7.96 seconds. Finally, all the speed that it loses on the way to its maximum height, as it loses 39 meters per second, it's going to gain all of that back on the way back down to the starting height. So the velocity at the end at the range position is going to be negative 39 meters per second. If you weren't sure how to do any of those things to sort of figure them out that way, the numbers that we definitely know at the range position would have been d equals 0, the initial velocity is 39, and we know acceleration is negative 9.8. With those three pieces of information, you could have used our kinematics equations to solve for VF and to solve for time. Once you would solve for time, you'd be able to use it in the x, and you'd be able to solve for distance, because distance is velocity multiplied by time. So that's every problem on the angled projectile review. Hopefully you understand what's going on.